Okay, we're going to start with review session 2. So this one has some different categories that are different from the first one. We have solubility equilibrium. We're going to do some more thermodynamics. We're going to do another electrochem. We're going to do gases. We're going to do liquids and solids and some chemical equations. I thought we hit the big ones to help us out as much as possible. Okay, so should be 6, but it's kind of like 5.5 because the equation one always is a little bit shorter. So hopefully we'll get through everything and see where we're at. So let's jump into it. I would definitely have some extra paper. We're going to kind of go in and out of working with what I'm writing versus what you're going to be doing. Kind of help you try to come up with some of the conclusions by yourself. So I'm not just doing that work. So I think it'll be a positive in the long run. Okay, so first question says answers 1, 2, and 3, weighting 20%. By the way, first 3 questions, it should take you roughly 20 minutes. Now, when I say that, that means you're going to have extra time. The last 4, they usually average about 7 to 10. So do think about that in the beginning. Like, man, it's taking a while. The first 3 should always take about 20 minutes or more. The last 4 should take around 7 to 10. At least that's the way they design it. And then you're still going to have extra time. But that's kind of the baseline goal. Several reactions are carried out using AgBr, a cream-colored silver salt, for which the value of the solubility constant KSP is 5 times 10 to the negative 13th. A, write the expression for the solubility product. So, see if you can come up with that. Again, you can work with each other, you can put your tests together. This is not class, this is us reviewing and getting ready as we go. You have to continually remember that a KSP, regardless of how it's written, if they give you another equation and it makes a solid at the end, that solid then will make and break apart, and that's how it's utilized. For example, I know this isn't the problem, but you could have something as simple as this, where you have NaBr plus AgNO3, which then makes AgBr plus NaNO3. Well, when you're all said and done, this is my solid right here. It could talk about solubility products and all of that, and yet you're like, well, wait, I don't understand. This is the one then that will drive up into here, and then we talk about still that equation, how much will actually dissolve versus what doesn't. So you're looking at a thing that usually precipitates. It's confusing compared to the other ones. I think most of you probably agree if you had a choice. KSP would probably not be the first K problem you'd ever want to do, but it's ones that we should try to learn as much as we can from. So anyway, just want to kind of point that out. It could stem from a lot of different kinds of looks. So I hope that you wrote something along these lines. There isn't much else to write. And that's a KSP, right? If you have a coefficient, you'd have to write that and all that good stuff. So 1 point is earned for the correct expression. Ion charges must be present, parentheses, instead of square brackets, not accepted. So if you're a sloppy bracketer, make sure you at least have something like that's not horrible, but at least I had a 90-degree angle at some point, so it's not a parenthesis. But I like that they said that. If it's not a parenthesis, it is wrong. Sorry, it's not a bracket, it's wrong. Okay, letter B. Calculate the value of Ag plus in 50 mils of a saturated solution. Okay, that's all it says. This is where people start to get confused. If you don't know what you're doing and you're doing a K problem, the minute you have a K problem and they're asking for an amount and you don't know where to go, if you don't at least start an icebox, you're doing a disservice to yourself. That's how I feel about it, at least. So if I just take this idea, maybe you're like, I got it, I know what I'm doing. It's great, but I want to really make sure we hammer a few things home today. So I would start with 0, and it starts to reveal itself really quickly then. Oh, okay, I want the concentration of my Ag plus. Okay, well, it's always asking that at equilibrium. Okay, oh, yep, here we are. That's going to equal x. Well, can I figure something out here? Reminder, either you know everything on the equilibrium line or you know your k. If you know one or the other, because k tells us everything we need to know about equilibrium as well, or we know everything on the line, we can figure out k, I can figure out the other. So I'm going to use my KSP. And in essence, it's this, right? But it really just becomes that. So please do be calculating these things with me. Like in the first one, I'll kind of get you into the mode. I know it's early, I know it's a Saturday. I think this one's not as tricky as some. Like if you had some sort of a exponent or a 2 in there, you really have to understand what you're being asked. Oh, and I didn't write it the way I'd like to write it. What if I asked for what is the molar solubility? What would be the answer then? The molar solubility of this compound. Same what? Molar solubility is always X. And I think that was when I was a student, that confused me. I never was really taught very well. Like, no, it's what dissolves. I'm like, okay, but what? They're different numbers and all that. What if it's a 2? What if it's not? The X always reflects the molar solubility. So kind of keep that in mind. It's the 1-to-1 ratio. Okay, so a little bit of math to start us off. A lot of this, there's not a lot of I's. Actually, only one of them has an I or double I in this one. A little unique. Usually they have a lot more than that. All right, moving forward. 50-gram sample of distilled water is added to the solution described in part B, which is in a beaker with some solid AgBr at the bottom. The solution is stirred and equilibrium is reestablished. Some solid AgBr remains in the beaker. Is the value of Ag plus greater than, less than, or equal to the value you calculated in part B? Justify your answer. Okay. What I'm going to do is I'm going to help in the beginning by drawing the idea of what's happening here, okay? So, and you don't have to, it's not requiring you to do this, but I'm just thinking out loud here. So I have Ag plus and Br minus going in here. The value right now, before we did this, is what we call a saturated solution, right? You have to understand, whenever we calculate this, this is the max. It's the max concentration. Like you cannot dissolve anymore. Whenever you're using solubility, well, how much can dissolve? The value, that's as much as it can go into that solution. We're not finding anything less. So if you found a number and it was less than this value, would more be able to dissolve? Yes. Oh, I want to dissolve this amount. Nope, it can only dissolve that amount. Okay? And that's concentration, so it doesn't matter how much is present. If you then, I didn't do this well. I'll have it higher, just not as exaggeration. So I'm adding my water, and I'm adding my Ag and my Br minus, and it said some still remains on the bottom. It's important, bless you. Here's my statement to you. Maybe we'll just kind of go all at once. All this is probably just excess to talk about, but what students will do is they will overthink this or underthink this in a way that they're not being able to place themselves. If I ever am confused, I like to actually try to physically see what's happening here. If this is saturated, the reason why it's important, the most important thing that they said in that, some solid AgBr remains in the bottom. What that means then is that I threw it in there, I stirred, and what? The maximum amount dissolved again, right? So it's saturated. If it said nothing lies in the bottom, then you don't know if it's saturated or not. So that's an important little comment there. what happens to the concentration of my Ag plus? Is it more, less, or equal? Concentration. Let's get this out of the way. Can more dissolve in more water? Can more just stuff, actual stuff, dissolve if you have more water? The answer is yes. If you have a little thimble, you can only dissolve a certain amount. If you have a big bathtub, you can dissolve more. But the problem is that this is a concentration. It's a ratio. It's moles per liter. Moles per liter. So, what's the answer? Less than, what's the options? Less than, equal to, did they say greater? No. Oh yeah, greater than, less than, or equal to. Anybody want to take a stab? I heard someone whisper, they're brave enough to go a little louder. Equal. It should still be equal. It's still saturated. The maximum, yeah, but it's in more water, yes? So there's more of that and there's more of that. The ratio is still exactly the same. So I'll read you what they have, but my explanation would just be because it's reached equilibrium again, the amount of moles over the amount of volume will be the same. It's still saturated. This value is the saturated amount. I'm probably not saying this as well as they did this time. The value of Ag plus concentration after addition to distilled water is equal to the value in part B. Concentration of ions in solution in equilibrium with a solid does not depend on the volume of the solution. Not loving that explanation. It's a ratio. It's saturated. The maximum amount can still dissolve, and that is the saturated maximum amount. I hope that somewhat makes sense. We got to keep putting meaning onto what KSP means, and the more you understand it, the more you see it in one situation and the next, the more comfortable you're just going to feel. Okay, so maybe I overkilled that, but it's only 1 point. All these things are 1 point so far. This isn't the most exciting first question to have, but it's an important one. Calculate the minimum volume of distilled water in liters necessary to completely dissolve 5 grams of AgBr at 298. Woo! Okay. What the heck do we do about that? So I have 5 grams of AgBr. Okay. Say that again. Calculate the minimum volume of distilled water in liters necessary to completely dissolve 5 grams of sample. Why is it saying minimum in water? Because if I have like the ocean, of course I'm going to be able to dissolve 5 grams of it, right? But what's the least amount of water that I can have that will still dissolve all this? So what is the value that matters? It's still this guy right here. That is the concentration that is maximum. Like you cannot dissolve any more. So that would be the most saturated, meaning the minimum amount of water as well. So you have to remember, it's moles per liter. What's it asking? The minimum amount of water. So I have to solve for L. So what should I do with that? Put in moles. If you're ever giving grams, if you're not even thinking, at least as an option of maybe I should put this into moles. Well, if you take a step back on a problem and go, well, moles would be involved in molarity, well, probably need to get this guy into moles. Now, yes, they do. Good. A lot of times, they do you big favors, and they actually tell you the molar masses already. The reason why they're doing that is they're trying to save you time. They're just trying to save you time. So that's real nice. And if they do that, by the way, they are giving you the answer basically by saying, hey, if you're not converting to moles, you're not seeing our clue. So I would do that first. And this is more of just being a savvy chemist, in my opinion, with the calculations. Can you just kind of take a step back and just kind of analyze what's happening? So if that's my moles, what do? Well, it's moles over liters equals molarity, right? What molarity do I want? The saturated value, right? So, I mean, how I would set it up, and some of you would do this differently than me, probably. I just moved it so 7.1 times. Right? Which is molarity, right? And when in doubt, my professors and teachers always taught me that sometimes writing moles over liters is just a better visual for you. Hopefully you get this. And if you don't want to write it like that, my gosh, you don't have to. You could have written 37,000. You're like, whoa, that's really big. These are insoluble products. These do not, and you sit here and like, why are we talking about how compounds that barely dissolve, and now we got to talk about what it takes to dissolve them? Because sometimes you do need to get these to dissolve, or you need to know how much is going to come back out. But just understand that it should be quite a bit of water to dissolve something that doesn't dissolve very well. They're basically insoluble, so you need a ton of water for that to happen. Okay, that's 2 points. 1 point is earned for the correct calculation of the moles, and then 1 point for the answer. So if you just got to the moles, my gosh, they give you molar mass and they give you grams. If you just go, oh, I need to do a T-chart, I'm good to go. You get 1 point for that. Okay. Any questions so far? And this one's kind of just mechanical so far, you know, just kind of, hey, next answer, next answer. There's not a lot of depth on it, although I do think C has a little bit of meaning, at least in that part. Let's keep plowing through the first one here. A student mixes 10 mils of 1.5 times 10 to the negative fourth molar AgNO3 with 2 mils of 5 times 10 to the negative fourth molar NaBr and stirs the resulting mixture. What will the student observe? Justify your answers with calculations. Okay, so when in doubt, get the equation. Okay, so let's talk about that. I have AgNO3 plus NaBr. Please finish that for me. You're going to obviously see the one that matters. Many of you might consider going in some different directions with this. I totally understand how you could do this in a few ways, or how to interpret this, but hopefully we can see what we're looking at here. So that's the one that matters, right? So what if this did not say supported with a calculation? What's the answer? What would a student observe? What's the answer? You're like, I don't know the equation or the reaction. They give us enough information. There's 4 signs of a chemical reaction always. You have to be able to, whenever they say what would you observe, it's 1 of 4 answers always. It's bubbles or gas, right? It's heat or light. It's a color change. Sorry, like I know this one. And precipitate, right? Okay, so we're talking about solubility products. It's precipitate, and I'd be specific. What color precipitate are you going to see? It says it in the beginning. It's a grayish tan, isn't it? Isn't that what they said right in the beginning? Silver or cream color. Cream color, sorry. Hey, you can interpret it as a grayish tan. So I'd say you're going to see a cream colored precipitate. Great. The problem is they said prove it or show it through calculations. So what I need to do is show that it precipitates. This is Q. If you have K's and you need to show if something's going to happen or not, and you might not have interpreted it like that, and I get it. So remember, KSP equals this times this, so Q will equal the same thing. Here's the thing. You guys, when you mix 2 things together, you need moles of your compound over total volume. And that is the mistake people will make, because your concentrations will change. So let's take a look, once you finish writing that, at the information that was given to us. It says that the 10 mils of AgNO3. Well, of that, that's the part that matters, correct? Like that's what we're going to get out of that, the Ag from the AgNO3. And then the 2 mils of the 5 times 10 to the negative fourth NaBr, we need that Br, right? Why I'm just underlining that is you got to be careful. What if that wasn't a 1-to-1 ratio? You have to take that into account. So what would that mean is if, just making this up, if this was double, the molarity value would be double, not the volume part, right? Because remember, like CaCl2, if the whole thing is 2 molar, Ca is 2 molar, Cl is 2 molar, and Cl is 2 molar, right? CaCl2, 2 Cls both get the molarities. So this is how I would do it in one foul swoop. Maybe you wouldn't, but here we go. I'm going to do the Ag. So this is what I have. I'm going to do millimoles. I'm going to do it all at once. So if you have molarity, here, let me just show you what I'm doing. So I have 10 mils of AgNO3 and I have this as a molarity. There are better looking ways than this. This is the fastest way to do this. So look what I did. On the top, I took the volume. Remember, molarity is moles over liters. So if I take my milliliters times my moles over liters, right? And I know you're like, well, no, you got to put that in the liters. Yeah, that's true, unless if I redivide by milliliters again, because then that's just gone, and I'm re-left with my new molarity. So I figure out how many new moles I have, and then I divide it over the new volume because it's diluted. You have to add your volumes. It's going to go down. Your molarity is going to be less because you are mixing it with something else. So what I'd like you to do, please put this other value here and find out the Q. Try to mimic what I have while I read about mallet 4, whatever this means. You band people know probably what I'm looking at right now. Play that funky music. I'm shipping up to Boston. It's a rockin' jig, it says. The only reason why we're doing this is that the phrasing was justify your answer with calculations. What am I justifying? That it's going to precipitate, and I want to show you what I'm trying to do with that. So So, is Q greater or less than K? Greater, right? Right? Slow down. Maybe you already have it in your head. I just want to go back up here for a second. This equation right here on letter B, what does that mean? We always just envision K's in the middle. It's not technically in the middle, but we see K's in the middle, right? So where's my Q right now? It's bigger on the number line, so it's to the right, correct? And which one always moves to the other? We always move towards K, right? We always reach K. So that means the reaction, whoops, wrong spot. The reaction is going to drive this way and make more solid. That's how I envision that. That's how I can prove this. Now, you don't have to say all that. If you ever had to say an extra explanation, you would just say Q is greater than K, which will drive it left, or which will create more solid, or will create the precipitate. That's all you'd have to say. Now, they're not even saying that. They just said a precipitate forms. They show the greater than, the Q is greater than K, and they just say a precipitate will form. I continue to try to kind of show you guys it's crazy that if you just say it like you know it, it's amazing how it comes across. Like, don't ever say, I don't know, I'm just guessing here, but like, why are you wasting that 5 to 7 seconds? I've read things like that. It's like, wow, I don't even know if I want to keep reading. You're clearly guessing now. And you don't get the benefit of the doubt anymore and something like that. So be careful. Say it like you know it. All right, almost done.
Hey, Mr. Rossi.
Yeah.
Where'd you get the K value from?
Yeah, you know what? And I regret actually writing it down because I was seeing if you guys were going to write down the times 10 and the negative 7. It gave it to us right in the beginning. If you look at letter A, I believe. Was it in A or before A?
Oh.
Before A? Yeah, and I don't know, maybe you wrote the other one, the one that we figured out. I should have actually waited, and once I wrote it down, it's kind of done. You got to be careful. The value we used here was just the molar solubility. That was the K, right? That's the KSP. So to make sure you're using the right one. That's a great question because I was thinking the same thing about if you guys were going to find the right one. 2 left. This is a long question. Again, 1, 2, and 3 are always big. They're long. They're worth a lot of points. And you can put stress on that and just go, okay, I'm just going to do the best I can. I understand they reset multiple times. I always have a chance to redo it. This problem, you could totally have gotten it right without having done anything else correct. You know, understand that stuff. By the way, holy cow. 1 point is earned for the calculation of the concentration of the ion. So by doing this, that's 1 point. 1 point is earned for a calculation of Q. So literally, because you did these two things, now they did it separately. We did it all at once. So this whole thing right here, that was 2 points. And then 1 point is earned for indicating that the precipitation, like that, because of this, it will precipitate. Holy cow, that's 3 points. So, yeah, something like precipitation, or precipitate will occur, or precipitate will form, or precipitation occurs, something like that, because of that statement. All right, 2 more. F, oh, I, double I like it. The color of another salt of silver, AgIs, is yellow. A student adds a solution of NaI to a test tube containing a small amount of solid cream-colored AgBr. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. I. So let's just make sure we understand what's happening first. I'm just going to, if you already had AgBr, I just want you to understand this because it's going to matter when we do the problems here. We added NaI into the test tube. So AgBr was already there. We just added NaI into it. Okay? So let's talk about that formula. And 2 ways you could write it. You could write it in a net ionic, or you do not. Unless if it goes out of the way, it's a net ionic. We do not need to do that. So I had AgBr there. I'm going to write states of matter only because I want you to see them. It does not say you have to do that whatsoever. So I want to see if you can, without me, this part's not the hard part. I want to see if you can do a net ionic with me on this. So what's made on the other side? This shouldn't be all that complicated. And why do I know what's made? Is because it says that the thing does turn to yellow, correct? It turns to yellow. What is yellow? It's the first sentence. AgI, right? So we know it happens. If you're like, well, wait, maybe they're tricking me, or maybe something else is going to happen. They're giving you confidence that this is going to occur, okay? And you know that that's a solid. So then the other thing must be together. How do I know what state of matter that is, by the way? What state of matter is that? It's AQ. Why am I very confident that it's AQ? Because there's it's a salt, and they're all salts. It's an alkaline metal, so it'll dissolve if it's in any kind of a liquid format. Can you guys, without rewriting it all, and separating it, could you cleanly give me a net ionic equation? Meaning a net ionic equation, we cross out all of the spectator ions, and things that are in solution have charges. Would you be able to do that? I'd like you to try. Can you do it cleanly? Think about, so visualize it first. What doesn't change? What stays in solution? Whatever is in solution but then wasn't, or was in solution, now it isn't. Those would have charges if they're an AQ on one side versus the other. If you're not sure, we'll see the answer in a second. That's a net ionic. Right? If you visually just look back, go, well, hey, Na is an AQ both times. So that's why that would be crossed out. Reminder, you got to have not only the elements balanced, the charges, and this one's very straightforward, but charges have to be the same, not zero. -1 on one side and -1 on the other, that's balanced. A lot of people get very uncomfortable. Well, it's got to be 0. Yeah, it's technically 0 because there's other ions floating around. There always has to be a partner. If you're like, where did it go? If there's a negative here, there had to have been a positive somewhere. It's just not showing up because it's not active. So that's just that's 1 point. You did not have to do the second part. But if it did ask you to do net ionic, which it totally could, they would ask you for simple things with double replacement reactions or single replacement reactions kind of approach. Double I last part, and we are out of here for this part. Which has the greater value of KSP? justify your answer. So this is what it's asking. Which one has the greater KSP? So, if you're not sure, let me remind you what just happened. You had AGBR, you put it in, and now it made AGI. And it's a little yellow. So, what does it mean to have a greater KSP? That's the root of this thing. What does that mean? Is it more or less soluble? Does it dissolve more or less? The greater the KSP. I know it's early, but is it dissolves more or less? Greater KSP. More. I don't know. I don't know how to answer that. Let's go back to this equation again. The greater a K, don't worry about me filling in the blank, Ka, Kb, Kc, Kp, Ksp, it means the larger the K, the more I'm to the right, correct? Always. So that means I have more ions. So it can dissolve. So if it doesn't dissolve, I have a smaller K. So by just getting your mind straight, you should be able to answer that question then. Which one has a greater KSP? Anybody? 2,000 extra credit points if you answer. Wow. No one believes me. I don't believe in myself. It's got to be that one. Reason why is the other one became a solid. If this was so soluble, it wouldn't be the one that's coming out of solution when it comes together. So that means this one is a greater KSP, because if it wasn't, it would stay as a solid. It was able to dissolve before the other one. So let me give you a couple explanations. It just says justify your answer. AGBr has a greater value of KSP. The precipitate will consist of the less soluble salt. When both I and Br are present, because the color of the precipitate in the test tube turns yellow, it must be AGI that precipitates. Therefore, KSP for AGBr must be greater than KSP for AGI. To be honest, the answer, they weren't assuming that you understood that AGI was in there. They just said it turned yellow, but that wasn't that difficult. They said AGI was yellow. So you just, oh wait, well, that's the solid. Well, reminder, the AG was floating around in there the whole time. There's BR and there's I. So all I had to do, one of them glommed down to the AG. Well, it ended up being that one, not that one. So the fact that this was more insoluble, maybe that makes a lot more sense seeing it that way. Like, I got AG no matter what. It glommed onto one of these two. Oh, it let go of the BR and it grabbed the I because it was less soluble. So that was actually just 1 point. All right, so that is that problem. And let's go on to the next one. Okay, so I put this up here so we can manipulate this a little bit. I thought it was good to visually see instead of just having it point blank. So this is a thermodynamic problem. I think these are really vital. If it's not a full problem, they always show up. You got H's, you got S's, you got G's. I think we'd all agree that we'd like to see a few more of these examples, see how we utilize how they all work. So answer the following equations using information related to the reactions X, Y, and Z in the table above. For A, or letter A. For reaction X, write the expression for the equilibrium constant Kp. Please do that. And if you want to compare with someone else, you definitely can. See if you can get it right. These are always usually 1 point, but it's all right or all wrong. So you have to be confident and know exactly what you're writing. So again, this is for reaction X, I believe. we're done, you can definitely look up. Brackets are wrong. If you include the carbon, it's wrong, right? There's that solid sitting there. Can't have that in equilibrium expression. Gases and AQ, gases and AQ. And if it's a KP, it's only gases. And you're like, well, what am I going to do with an AQ? It will never ask a KSP with AQs and gases at the same time. It would be a KP will be asking about ones with gases. Just understand that. Letter B, for the reaction X, will the equilibrium constant KP increase, decrease, or remain the same if temperature rises above 298? Okay, this is not a simple just, oh, I don't need to look at an equation. Whenever temperature goes up, it speeds up the reaction. That means it's always going to make more things. What does the temperature relate to on this board? Temp relates to that one, right? You have to understand if it's in your phrasing, does it say justify? I'm assuming it probably does. You have to use the word, it's exo or indo, so it will cause it to go blank. That's what you need to say. But we need to physically put E on left or right. You cannot say that though. You can't be like, well, the E is on the left, so that's, it will do that. It doesn't actually have meaning to it. So where is my energy? Left or right? Reactant or product? So it is X. We're still talking about X, right? So I have positive, so it is on the reactants. I'm going to actually physically write it there. It is on the reactants, correct? So by increasing the temp, the reaction will go to the right, which causes my K to increase. My justification, I would literally say the reaction is endothermic. By raising the temperature, causes the K to go to increase. I will read what they say. It's always good to hear it. If the temperature is increased for an endothermic reaction, then by Le Chatelier's principle, the reaction will shift towards products, thereby absorbing energy. With greater concentrations of products at equilibrium, the value of Kp will increase. That's a lot. You probably don't need to say all that, but you would need to say something. I would say that according to the enthalpy, or just say reaction X based on the information is endothermic, increasing the temperature will cause it to create more products. Increases the Kp. That would be the most, the largest explanation that I would give. You may not need to say all that because it's only a point. One way or the other, it's only a point. All right, let's keep going and seeing these relationships. Letter C, for the reaction Y at 298, and they're all at 298, is the value of Kp greater than 1, less than 1, or equal to 1? Justify your answer. Interesting. So, what is it if it's equal, greater than, or less than 1? So what it's asking is this idea of 1, okay? Is it greater than, less than, or equal to? Think about this for a second. For letter Y, what does it mean to be 1? It means that in my KSP, the values on the top, I think there's 4 of them here. The values on the bottom would be exactly the same. And I know there's actually pressures, right? So they would have to be exactly equal. Okay. If it's less than 1, it's greater than 1. What does a greater than 1 mean? It's greater than 1. That means it's product favored, right? If it's less than 1, that means it's reactant favored. And if it's exactly at 1, it's not at equilibrium. They're all at equilibrium, but like nothing's favored. It's reactants equal my products, right? So, can anybody come up or give me a suggestion of what I'm looking at? Again, this whole table's giving me information. What is the sign that tells me this idea of where it's probably favored? I'm not even going to write that on top. This is what it's saying. Which one is the one that gives me that information? Any thoughts? Yeah.
Can you look at the temperature and like whatever side of it drives it towards?
You could, but the problem is it is already at that temperature. So all of these are at 298.
Oh.
You know what I mean? It's a good idea. They're saying though at this position right now. Which one does it? Change an S. So disorder Maybe. Here's the issue with that. You are at 2 and there's 2 here and 2 here, but they do have a value already. So it's not asking like, does S increase or decrease if something occurs? Yes, it's actually saying I am gaining disorder. So what are you saying? You're going more to the right or more to the left? What is the one letter that is the ultimate guide of whether or not a reaction is going to happen or not? G. Okay, let's talk about that. What does that one mean? If it's positive, is that spontaneous or not? Now, if you're like, but are these reactions happening or not? They're happening. Sometimes there just needs to be some extra intervention. What that's saying then, this is the interpretation you need to get out of this, is if it's positive, that means it's not naturally going to the right. It's actually going back that way. That's where you have to go with that, okay? So you just have to have that interpretation. The change in G is positive, which means that the reactants are favored. That's all you'd have to say. Because if you flip the reaction's going to, like all these signs flip, right? Every single thermodynamic sign, if you flip a reaction, those signs flip. So my response to that would be positive G is non-spontaneous. Kp will be less than 1. So positive G means it's non-spontaneous, which indicates the reactants are favored. So Kp would be less than 1. Okay? So please understand, if you're ever not sure, Ks and Gs, they link together quite well. What letter is this? Letter C. Positive G results in a non-spontaneous reaction under standard conditions. This favors reactants over products as equilibrium is approached starting from standard conditions resulting in a Kp less than 1. There you go. 1 point. D, we're almost done. Oh, oops, there's a big F yet. For reaction Y, which is larger, the total bond energy of the reactants or the total bond energy of the products? Okay. This is the one thing I always find. This is actually probably why, I can't remember why I pick every one of these problems, because sometimes if they stay for a couple years and I still like them, I kind of forget why, but I am feeling like C and D are the reasons I picked, so that's the last one and this next one. Bond energies. You're actually breaking a bond. Like via water, don't write this. You actually have to break these bonds, right? You got to break them. So if you're talking about an equation, this is not products minus reactants. Bond energies are about breaking and making bonds. Bonds have to be broken. You have to break bonds. And then you have bonds that have to be formed. Okay? That is the order, by the way, right? You have to break them before you make them. So, of all of these, by the way, which one reflects bond energy, do you know? The actual act of breaking the bonds. You have to put energy in to break those bonds. Anybody know? Change of H, yes. Perfect. That's the energy that goes in. So that is the one. Are we reaction Y yet? Is that what we're looking at? I think. Is that right? Okay. So that's change H. Can't be disorder. Well, yeah, but if you're breaking them, that's true, but that's not what we're looking at. And this is the ultimate relationship of both of these, right? So that can't be that. So process of elimination, you might have gotten there if you were not sure. So you just have to look at that number. If you're sitting there, I don't have the numbers. I don't have all the bond energies. You're not giving them to me. Right. They're seeing if you can interpret the idea. So because it's positive, what does that mean? It means, just think of a bank account. I have more than after I put in some money and I took some out and I still have leftover amounts, right? So which one is bringing energy to the table? Breaking or forming bonds? Which one puts energy in? Think about it. You got to break them. You got to put energy in to break a stick. Okay? So this is where you're putting the energy in. So energy goes in, right? Energy out over here. Wow, this is so eloquent. So which one? Do I have bonds broken or bonds formed? Which one do I have more of for the energy? Based on positive, was it plus 41? What does that mean then? What am I going to do? Am I going to do greater than? Oh, come on. Greater than? Or am I going to do less than? Which one goes there?
Greater than?
Greater than. I should have more. So, what's the answer then? If I word it the way they want. Total bond energy of the reactants or the total bond energy of the products? Which one has the reactants? It's larger. Well, wait, but one's breaking, one's forming. Guys, if you break it, let's just say, make up a number. It takes 100 kilojoules to break this one bond. You know what? It releases 100 kilojoules when it makes that same bond. When you break a bond, you put energy in. When you create a bond, the energy is released back out. Okay? So it doesn't matter the idea of like the value. The value is the same if you're breaking or making. The issue is that you're not breaking and making the same exact bonds. You're creating new bonds or breaking different bonds than you're making. So that's where I reference that. So let me read what it says though. It says total bond energy of the reactants is larger. It's endothermic, so they wrote the number, plus 41. So there's a net input of energy as the reaction occurs. Thus, the total energy required to break the bonds in the reactants must be greater than the total energy released from the bonds are formed in the products. All right. 2 more. That was 1 point. Again. E, the following statement, true or false? Oh. Okay. On the basis of the data in the table, it can be predicted that reaction Y will occur more rapidly than reaction X will occur. Remember, these usually are trick questions. And chemistry is not about tricking you, but they're trying to see if you truly understand things, okay? So, what I'd like you to do, it's true or false on the basis of the data, and you probably need to justify your answer, probably a sentence to explain. On the basis of the data in the table, it can be predicted that the reaction Y will occur more rapidly than reaction X will occur. Okay, the reason why they're pointing you towards these 2 questions, by the way, they're trying to get you to look at G. Just saying no. First off, it's hard for me to even have a conversation about it because they're both positive. But even if they were negative and you had different numbers, that is just about if it's spontaneous or not. Spontaneous is not about speed. So this statement is false. This is not about speed. Thermodynamic data for an overall reaction have no bearing on how slowly or rapidly the reaction occurs. Done. There's no indication about time. And be very careful. Spontaneous sounds like it's about time. It isn't. It's just will it naturally occur or not? Is it naturally a favored process? So this is false. I mean, you could say something like all the data above has no implications on time or speed. Okay, so that's false. Just 1 point. All right, 3 last little I's, and then in the next one, I'm going to have you guys kind of work back and forth with me on the next one. Consider reaction Z. Oh, finally, we get to make our own numbers. Is the change of S for the reaction positive, negative, or 0? What do you think? Anybody know? So S is disorder, right? So basically you have to determine if it's becoming more disordered or less disordered. I don't like to say the word ordered because it's about disorder. So what am I going? Well, let's just take a look. You got 2 moles of gas, right? And now you're going to 1 mole of solid and 1 mole of gas. So that is becoming what? Yeah, it's becoming less disordered, right? Or more ordered, but that gets confusing. So that's definitely negative. Correct. You do have to say a justification. Guys, keep it simple. It went from, the reaction went from 2 moles of gas to 1 mole of solid and 1 mole of gas. If you feel like you need to say more, I just say that that's becoming less disordered. Let me read what they have. It's always, again, nice to hear. It's negative in reaction Z, 2 moles of gas with high entropy are converted to 1 mole of solid and 1 mole of gas, a net loss of 1 mole of gas and thus a less loss of entropy. Or you could say reaction Z can be obtained by revert. We won't go there now. Double I. 1 point. That was 1 point. Determine the value of change of H. What? I have to find the value. Anybody figure out how I would do that? I'll do it with you, but anybody have a gut feeling of what you see with this? So I need to find change of H. They didn't give me bond energy. Shoot, I don't have that. Then you have.
Would you use X and Y and do two equations for that?
What's that called?
Average?
No, but you're there. That's what we're going to do. Hess's law. If you ever see a reaction like, man, you know, there's parts of it here, and there. Oh, if you're ever dealing with H, and it asks for you to solve a new H for a new equation at the end, and you have H's for other equations, just take a step back and ask yourself, could you flip these, multiply them, divide them, and do they all have them in there? If they do, that is Hess's law. It just is. So let's take a look. What do we need to do on this? What I would suggest, you have to look for what's in here. So here's my CO, here's my CO2, and here's my carbons. Okay? To be honest, I actually don't like that CO sitting there because there needs to be two of them, but I guess maybe they're on the right sides. We'll find out, or maybe not. This has to get on the other side, correct? And so does this. So it looks like I gotta flip both. If I flip both, it actually gets my COs to the other side, and I needed two of them. So it looks like I don't need to do anything with magnitude. I just need to flip them both. Because if I do, I'm going to get 1, 1, which is 2, one of these and one of those. So you do need to show the work. You wouldn't necessarily have to write it all out, but you would have to do negative 131 plus, is it negative 41 now? Is that right? Point. Technically per mole, if you ever forget the mole, per mole, that's okay. And last, but certainly not least. A sealed glass reaction vessel contains only CO and a small amount of C. The reaction occurs and the temperature is held constant. Will the pressure in the reaction vessel increase, decrease, or remain the same over time? Okay. You gotta make sure you understand it. Usually I always read these twice. So I'm like, okay, let me start over. Sealed glass vessel contains only CO. So I only have CO. When in doubt, write it. Draw it out. A small amount of C is added. If reaction occurs and the temperature is held constant, will the pressure in the reaction vessel increase, decrease, or remain the same? Okay, wait a minute. So they're just taking CO and adding C, right? Right, they're taking CO and they're adding C. Okay, that's not an equation I have here. So, anybody have any thoughts of what is happening? Oh, did I read that wrong? It has both already, doesn't it? I'm sorry. I'm sorry. Okay. You have C, O, and you have C. So what you have to do is you have to utilize the equations that you have here. So regardless of which one you have CO and you have C, and you're going to add temperature to it. Will the pressure in the reaction vessel increase, decrease, or remain the same? What you need to figure out is by increasing the temperature, one of these reactions is either going to drive it to the right or to the left. And why are you going to know if it's going to increase or decrease the temp? Will it make more gas? Will it be making more gas, or will it be making less gas? So, anybody have any thoughts? Will it make more or less? Will the pressure in the flask increase or decrease, or remain the same over time? Any thoughts? Okay. Because this is I, double I, triple I, what a reaction if you're confused on which one you're looking at. Which one would we probably be using? X, Y, or Z? Based on what we've been doing. Z, okay? I, double I, triple I, we've been talking about for the last 2 weeks that those usually relate really close. A's and B's sometimes. So if I just look at it, you go, well, wait a minute, the one's on one side, one's on the other. Yeah, it's called equilibrium. You can have it any time you want. So you have these two. What are you going to use with temp? You got to use the enthalpy values. So we just figured it out. That's why they made us figure it out. What was the final answer? It was negative, I believe, right? So that means energy is where? On the right. So by increasing temperature, the reaction drives to the left. So what is it going to make? Is it increasing temp? I'm sorry. Yeah. If the reaction and temperature is held if a reaction occurs and the temperature is held constant with the pressure in the reaction. Okay, I'm sorry. I'm confusing you a lot here. What? It's not changing the temp. I read it wrong. I'm struggling reading a simple paragraph. Let me try one last time. And the temperature is all constant. I kept reading that's an increase. But the pressure in the reaction vessel increases. The reaction proceeds. That's what it's saying. Let me get through this now. It's not about temp. I am so sorry. It did not say I'm increasing temp. If the reaction proceeds and it's going to occur, then does it make? Let me get rid of that. More or less gas. It's just going to proceed. It's going to make less. It's saying the reaction proceeded. It's saying like it's spontaneous. Okay. It drives it then to the right. That's what has to be interpreted, and I'm struggling reading that. Oh, so you had some C, you had some CO, and it said a reaction occurred. Well, that means that it's going to be going to the right. It's going to be making CO2 gas. The problem is you had 2 moles of CO. You only have 1 mole of CO2, so you're making less moles of gas. Oh, God. Let's just move on. 1 point. I'm sorry. I was like putting in extra words. Oh, you're stupid. Okay. We're going to do one more and then take a little quick break, make you get up and walk around a little bit. So let's get to some electrochem. I am wanting us to kind of compare and do a little work together on this one. I think it would be really healthy, kind of see where we're at. If you see a picture, these are really important that we're understanding everything that's happening in there, so I'm going to get us started. If you haven't, oh, shoot, I hope that's on there. You might want to use your orange sheets. There is one equation that potentially is on here. Because this is a little bit older, again, sometimes if it's not on there, they don't expect you to know it. Actually, Ben, can I just see something before I get to it? I always forget what's on it. Okay, so they give you this drawing, okay, and they have this really long equation. Please note, this is unique. This is a long time ago, so you're probably not going to completely remember this. When you see platinum, that is a generic electrode. For example, like they react hydrogen through here. Well, you can't have an electrical circuit connected to hydrogen gas. It's got to travel through a metal, but it's more of a placeholder. You'll notice you don't see PT in any of this, right? You don't see the PT. So what's happening is the reaction, which is always a redox, gaining and losing electrons, are happening in this case between a bunch of ions in the solution. The metal's there as a conduit, as a facilitator to help the electrons travel. Okay, but they're not the ones that are gaining or losing. They're like Switzerland. Okay, they're not going to get involved. So it says a galvanic cell. The minute I see that, that links to voltmeter, by the way. A galvanic cell means that it's naturally going to occur. It's going to, you don't need to jump in there and add energy or anything like that if you don't remember that. And it says the Valence equation for the spontaneous, hey, there you go, spontaneous cell, so it's naturally occurring, are shown above. The 2 reduction half reactions for the overall reaction that occurs is in this in the cell are shown in the table below. So you're given some values. It's really nice. We don't need it. I also like that. I know that I'm going to use those within this problem. Okay? A. On the diagram, clearly label the cathode. Okay, please, you just write cathode on the right or the left. Can you remember or talk to someone else? How do I remember cathode? I need to think about redox. Who's gaining or who's losing? Okay? So, I'll give you a second to compare with that. And then you can go right to B, calculate the value. So what you need to do is you need to figure out the value of the voltage. And can you remember how to do that? Be totally honest. Actually, I'm going to let you go through A through C right now. You should be able to get through all three. And if not, you work with someone else or listen in or whatever. So try to do all three. I'm going to pause it if you're at home. If you're not sure what you're supposed to be doing, you should look at the balance equation. The balance equation gives you a hint of the flow. If you're like, there's so much, you don't need to understand all of it. You just need to understand enough. Use the half reactions in the overall reaction. I'll give you a hint on this. You have electrons here. They both can't be on the same side. So one of those two reactions got flipped. What are both those reactions? Those are both the reductions. It even gives me a hint right there. It says reduction half values. I need to make one of them an oxidation. That means that electrons have to be on the other side for that. Okay? So you just have to figure out which one got flipped. And because of that, if you don't remember what a cathode is, we'll figure that out in a second. Is anybody able to tell me, actually, which way the electrons are flowing? Left to right or right to left? Are they going clockwise? Or are they going this way? Or are they going the other way? Anybody know? Think about it. You're gaining or you're losing. So if I'm going this way, let's just say it's this. I'm not saying that it is. This side's going to gain. So what does that mean? Where do my electrons have to be? Right? Reduction involves gain. So electrons would be on the left side, correct? Oxidation involves loss. So whichever one is flipped, the electrons are leaving them. So if it's the other way around, great. Then this would be the oxidation on the right, and this would be the reduction on the left. Well, what happens at a cathode? Reduction or oxidation? Reduction, a red cat. You know an easier way, and you probably don't remember this at all? If you can figure out the flow, it always goes in alphabetical order. It goes from an anode to a cathode. That's the way I remember it. The battery goes in alphabetical order. So can anybody tell me which way do the electrons go? Which one did I have to flip? And that's the one that's losing the electrons. Which one gets flipped, the top or the bottom equation?
The top.
The top. And you're like, how did you figure that out? Here's Fe3 plus right here. Just find one thing, right? One thing. Fe3 plus is on the right. Whoops. It's on the left there. That one got flipped. That means they're losing the electrons. Done. Right? The electrons are flowing this way. Immediately then, this is my cathode. If you're like, how would I write that if I can't just draw it or I can't label it? You could say the right cell is the cathode, or you could say the Mn2 plus MnO4 cell is the cathode. I mean, you could label something that's specific. But that's the cathode, right? So this would be the anode. It always goes from anode to cathode. It's not left to right, right? That's not how that works. So letter B, it says calculate the standard potential. Well, you should have been able to figure it out based on this equation. But to me, there's an easier way to do it. We always want the maximum voltage, right? You have to flip one. You have to, because they're both gaining electrons. That can't happen. It's called redox, reduction and oxidation. One has to lose, the other one has to gain. So what do you always do? You have to flip the one that causes the overall answer to be the largest number possible. So they might both be negatives. They might be a positive and a negative. If it's a positive and negative, that's the easiest, because obviously you flip the one that's negative and make them both positive. But if they're both positive, you flip the smallest answer, right? That's just how it would work. But what about magnitude? Doesn't work that way. So that's just a negative. I don't know if it has to show your work. It says calculate, but that's the work right there. And all these are 1 point. I'll tell you when it's not a point ever. How about that? So, anybody want to tell me how many moles of electrons are transferred when 1 mole of MnO4 is consumed in the overall reaction? Why do they say it like that? Because if you look, by the way, they're saying 1 mole right here. So it's in reference to this equation. So this equation, from these half cells, how many electrons are being transferred? So what do we keep talking about? What has to always be equal in each reaction? The one thing that has to be equal in both reactions, we need same number of electrons, right? You need the same number. So if you had like 2 electrons in one and 3 in the other, you'd have to do a magnitude of 3 and 2 to make them 6, right? Well, 1 goes into 5 nicely. So you can't lose 5 and the other guy only gains 4 and be like, we're good, don't worry about it. Like you have to gain and lose the same amount. So if they're giving up 5, they have to be gaining 5. So the answer is 5 electrons. The answer is always, when you balance it, you are lying there with the same number of electrons. I hope that makes sense. Like if that top one had a 2, what would be my answer then? Like in the beginning. What if that was 2 electrons? What would it be? Would it be 10? Wouldn't it? Least common multiple. It would be 10. Okay. Letter D. And I'm sorry for this one. It says calculate the value of the equilibrium constant KEQ for the reaction at 25 degrees. Explain what the magnitude of KEQ tells you about the extent of the reaction. I want to talk about what it means, but this is what. It's called the Nernst equation. It's not on your orange sheet anymore. It used to be. Just write this down. And that's why I'm apologizing. But there is a couple good points that we can still talk about. So please understand, this actual equation is not probably going to be involved unless they say, given the equation, please discuss this. There are 2 things, though, you should still be able to do and understand. Okay, so first, what would N be? N is always P equals N or T, that is moles, right? When I talk about moles in a problem like this, what am I referring to? You know, electrochem. I mean, I got all these things going on here, but what's the moles? My electrons. I have 5 moles of electrons. That's all that matters. So this is moles of electrons. Okay? Energy is my voltage. So those 2 things, if they ever do come up in electrochem, N, if it ever asks for moles of anything, that's electrons. And if it ever asks for the energy, that's your voltage. Okay, so if we just plug this in, we're pretty good to go. I have a 5, I have a 0.72 volts. And then don't worry about all this bottom value. This number is shortened after a couple other calculations. So if I have that part equals 61, and then if I get rid of the log, I'm just going to give this part to you. I want to discuss the ending. Boom. So just get the N and the E, like that's important. So, just so you understand, and again, this problem will not occur this way. 1 point is earned if you understood, though, where the voltage in the moles would be. Just FYI. 1 point is earned that you got this, and now 1 point is going to be earned to say, let me read it before I not had a good track record this morning. Explain what the magnitude of the K tells you about the extent of the reaction. The magnitude, so they're talking about the literal size of it. What does it mean for any problem? Don't worry if you're in electrochem right now. If I give you something times 10 to the 60, what does that essentially mean for a reaction? What's that mean? A K.
It's far to the right.
Really far. So it's basically going to go to completion. That would be a really good word. That would not make you have to explain a lot. The value is so large that the problem or the reaction goes to completion. If you really want to make it sound even better, you could say it will essentially go to completion. Basically what we're trying to kind of learn in first year chem is that all reactions kind of lie somewhere in the middle. You know, there's a little gray area there, but it basically goes to completion, right? It's such a large one. This reaction's going to go. So it's probably a really good cell because it's going to use up all that energy, right? It's not going to have anything left over. it's going to go. It's going to go to the right. That would be the last point. So because the magnitude is very large, the extent of the cell reaction is also very large, and the reaction essentially goes to completion. Look at that. Once in a while, I sound competent. Okay, it resets. So again, if you're getting really frustrated or you're confused, don't let that happen to you. It says 3 solutions, one containing Fe2+, one containing MnO4-, and one containing H+ are mixed in a beaker and allowed to react. The initial concentrations of the species in the mixture are 0.6, 0.1, and 1.0. Whoa, there's a lot of information there. Letter E. When the reaction mixture has come to equilibrium, which species has a higher concentration? So it's actually literally asking this, by the way. Okay, let me say that again. When it comes to equilibrium, what does that mean? It means that it's reached its end point, right? What did we just say? This reaction really goes far to the right, correct? So just look at the equation, like the main equation. Which one are you going to have more of? Look at the actual big equation. And if it says explain, it's because the reaction goes to completion. It lies far to the right. So who's to the right? The Mn2+? Yeah. So, because the reaction lies far to the right, the reaction is heavily product favored. Right? You can say it any way you'd like, but that's what it is. 1 point is earned for the choice of Mn with an explanation, including only one item. So listen to this. You have 1 point is earned for including 2 in the explanation. Let me give you what they've written. They said Mn will be greater because 1, as indicated in part D, the reaction essentially goes to completion, and 2, there is more than sufficient Fe2+ and H+ to react completely with the MnO4. Okay, I didn't talk about that part, but shoot. If you look at the actual equation, they give you 0.6 molar of that, and 1 molar of that, and 0.1 molar of this. If you look at the ratios, neither of these are going to run out. So that's why I know by having all these, it goes to the right. So I might have left a point on the table if I was doing this one. I think I would have rushed a little too quickly on this. You would have gotten 1 point for just saying, yeah, it lies to the right. You would have gotten 2 points, which I have a feeling this year most people did not get the second one. And it's not tricky, it's just you don't always think about it. So let's just make sure we understand. If they go out of their way to give you some values, just take an extra breath and think about, okay, why did they give me these? It's excess. I have plenty just because of the ratios. You could do math, but it's not asking you to do that. Okay, so that would have been on me. I would have probably gone a little too fast. But that would have gotten you to 2 points. So go to completion and excess H+ and F2- consuming the MnO4. Last one. Then we'll take a little quick break. When the reaction mixture has come to equilibrium, what are the molar concentrations? Whew, okay. What are the molar concentrations of Fe2+ and Fe3+? So, just understand this. These are the ratios on the left and on the right. I'm just saying. So, I have this is the tricky part. Is if I have, let me just show you how I did this. They did it very differently. If I have 0.6 molar of that, which is what they gave me, right? And they gave me 0.1 molar of this. And why am I doing this one? Because the hydrogen is like crazy big. It's 1 molar, and there's 8 of them. It needs 8, and I'm not going to go down that path. You need to figure out how much is used. How much of this is used before it makes that Fe3+ and the 5. So this is a little stoic. I'm kind of doing an icebox though. The way I did it, I thought it was kind of an interesting, easier way to do this. But see if you can understand this. So if I'm kind of assuming that this isn't like 1 liter, which usually they are. It's 5 of these for every 1 of these, right? So I need 0.5 to react with that. Does that make sense? Like 0.5 of this is going to get consumed because this will run out when it reacts with 0.5, like an equal ratio. So if I subtract 0.5, that's how I got that answer. I don't know if that makes sense at all to you, but I tried to not make it nearly as complicated. I'm saying, okay, wait, it's going to make the other stuff. So this is going to create that. Well, it's kind of like an acid base. One of these is going to completely get consumed, so I just did a ratio, or a mole ratio of how much. I figured out this is going to be the less of the two just by looking at the 5 to 1, and it's 6. This is 6 to 1. So this will require 0.5 of that, and that's why I subtracted it. This will be 0. Okay. And then I have nothing in the beginning, so that will transfer because it's a 1 to 1, and it's 5 to 5. That makes 0.5. 2 points though. 1 point is earned for the correct setup, including the correct setup for an equilibrium calculation, so any kind of an idea of a relationship, and then 1 point is earned for the numerical answers. I think, to me, that's probably the hardest part on there, and I don't think many people probably ever got close as a whole average compared to the rest of the problems. I'm sure people got it right, but not compared to those other ones. Okay, so if you have any questions about those and you want to go over it a little bit, we definitely can. Go get some water, take a walk, quick. Let's come back in 4 or 5 minutes, or 3 or 4 minutes, and we'll finish up the other problems. Okay. Next one. I always like to do these problems, gas problems, because they show up a lot. Usually we should be really good at it. The problem is there's little spots and parts that can get really confusing really quickly, and I want to make sure that we are understanding it. So I wrote this out here. It says a rigid 5-liter cylinder contains the grams of those two. It says calculate the total pressure in ATM of the gas mixture at 298. Not that you should have to see this, but just humor me with this. Just understand, like, that's your volume, right? You got your temperature right here, right? You want pressure. So what do those two give me? It's got to be moles, even if you don't see it. The fact that those are grams, that's my N, okay? So I'm telling you now, every PV equals nRT is always worth 2 points. It's either setup or something you have to do, and then if you're putting everything in right with the proper units and the proper setup, okay? So you should have an idea about this. Here's the issue, and I'm going to give you a little bit of a hint. It says total pressure. So these are in the same container. So right now, could you find pressure of just one or the other? Would you have enough information? You could do pressure of, like, you could do pressure of nitrogen, right? And then you could do pressure of oxygen. What would you do then? Add them together, right? Dalton's law. That's one way. It's totally right. The other way, I'm going to give you them all. If I do this, you could do that as well. You could add your moles first, and then do a PV equals nRT once. All are legit. Please pick a route and calculate it. So I'm going to pause it. If you are in the school of thought, or just where your mind went that you just calculate it and write down the answer, just understand that if you're ever asked, or you're being pushed towards probably solving for moles, the T-chart in the work is sitting there for a point. It's 1 point for moles of N2O2. Must show ratio of moles and mass and molar mass for both elements in the calculations. hence a T-chart. If you didn't, you lost some easy points for you. Like that would be a waste. I don't know which one you went towards. Personally, for me, I don't think I want to do 2 PV equals nRT if I already have these. That's just where I would probably be. So I would probably just do a total. And this is the way I would show it. And wouldn't necessarily have to do it this way, but I don't know how it would go much faster. Three sig figs. Try to keep doing that. And I'm not good at reminding you. I know. I don't think about it all the time, but hopefully that's been something that's been happening for you. Okay, so that's 2 points, always. 1 point for the moles, FYI, on that one, and 1 point for earned with the 8.56. Letter B. We have not seen this in an extremely long time, and we literally touched on it one time. But you still should be able to answer it just by the description of the name. It says the temperature of the gas in the mixture is decreased to 280. Calculate each of the following. The mole fraction of the N2 in the cylinder. Okay, first off, don't worry about the temperature in that one. You're like, oh no, now what happened to my moles? It's not like you have a coat on and then you go out in the cold and now your coat got smaller or larger. I mean, it's not like, oh my gosh, my car, it's cold out there. Oh, hope it has all of its wheels. It's not about losing mass or temperature. It's not in that reaction. It says mole fraction. A fraction of anything is something over something else. And usually it's in a percentage, let's say, it's a part over the whole. So if it's a mole fraction for nitrogen, and in this case it doesn't really matter which one it would be, but it's how many moles you have of one thing over the total amount of moles. But you got to show your work like that. Now what's confusing is like, but they're the same number. Think of this as this is the nitrogen, and the oxygen. Did I do it wrong? Is that what I did? Sorry. And then you just make it more complicated by following what I did. So, obviously in this case it's 50, right? What's the unit? There is no unit. It's a fraction. It has no unit, which feels really weird. So if you got 0.45 or whatever, 0.45, 0.50. I know it should be 0.500 probably, but no. 1 point earned. Okay? All right. Double I. Says the partial pressure in ATMs of N2 in the cylinder. The partial pressure of N2. So I only want of N2. So this is N2 at, I just want to make sure that, you don't have to write it like that. I don't want to be confused in what I did earlier potentially. So this is of N2. So partial pressure at N2. So let me get you down this line. That's why I did that, I think. The temperature change. The volume doesn't, because it said rigid. By the way, if that's why you're always wondering, like, why do they always say rigid? They don't say rigid and you're in like a balloon, the volume will change. Hope that makes some sense. Like, you'd have to actually worry about that then. What am I doing with the parenthesis I haven't written? Anybody? And there's 3 ways we could have done this. So this is the one that I go with. What do I write there? Is it the 1.7 or is it just the 0.875? It's just the amount, because it's asking just for nitrogen, right? So I want to just know the answer with nitrogen. Now let me throw out a couple other ideas. You could have done the total moles and then multiplied it by the mole fraction. Okay. And there's one other one you could have also done as well, is that you could have done the pressure, you could have done Gay-Lussac's law, which is this. Now, I'm not expecting that this probably was at your forefront. It wasn't for me. But if you put the pressure that you had initially, now this is assuming you already found the pressure of the only the nitrogen. Because you could have done pressure of nitrogen and the pressure of the oxygen, right? So if you already had the pressure of the nitrogen, You could have plugged that there over 298. Now it's 280 over the pressure. But my mind did not go in that path. I'm in PV equals NRT mode. So you could have done any of those, and you would have gotten, sadly enough, 1 point. Was it 4? You had 4? ATM? 1 point, sadly enough. Letter C. Says, if the cylinder develops a pinhole-sized leak, and some of the gaseous mixture escapes, would the ratio, okay, I'm glad this is in this problem, because you have to just realize how they sometimes phrase things. Would that ratio increase, decrease, or remain the same? Okay, reminder, when it talks about a pinhole-sized leak, it's about effusion. And effusion is about gas leaking out, so like a tire or a balloon. And it's, which is faster, lighter or heavier? If you had to guess, the lighter one is always faster, okay? Because it can get out of the holes easier. That's usually the biggest deal of all that. So lighter. So if you look at that, does this ratio increase or decrease? Which one's going to be decreasing faster? Which value? N2. This is going to go down more than that one, right? You're going to lose more of your N2. So my ratio decreases, correct? Because my top number is going to get smaller. So you have to interpret it in terms of that, which is kind of frustrating because it's like, well, if you flipped it the other way, I'd say increasing. What's the point of all this? You just understand the ratio. So the ratio will decrease. It does say justify your answer. I would say N2 will effuse faster than O2 because it has a lower or a smaller molar mass. And then I don't know how much more you need to literally explain about a number being above another number. And then because of that, the math. Let me I will finish what they wrote though. Thus, in the cylinder, the moles of N2 will decrease faster than the moles of O2. That doesn't say anything more about the ratio. Okay, 1 point. D. Okay, they reset. Maybe. A different rigid 5-liter container contains that many moles of NO. A 0.176 mole sample of O2 is added to the cylinder where a reaction occurs to produce NO2. Write the Valence equation. Totally unrelated to all this. They just told you all of it. Can you interpret right now and write that? Read what they said. Think about where it is. You should be able to do this. This is not high-level chem because they told you all the parts. But write it out, and I believe it needs to be balanced. So make sure it's balanced. And you're going to guess this is probably worth 1 point. But can you do it? Hope you got it. Let me reread it. It says, contains NO. A sample of O2 is added, where a reaction occurs to produce NO2. So these two are added together, the reaction makes NO2. Letter E, last part. Calculate the total pressure in ATM in the cylinder after the reaction is complete. What? Okay, so a couple things here. Total pressure. A couple ways you can do this. We're going to do this differently than, actually, let me see how they did that once. That's interesting. Okay. Pressure, I was using PV equals NRT a lot, but this is what I need to know. I need to know what do I all have here. So, what did they give me? They said, okay, they said that they gave me, so, by the way, if you haven't figured this out yet, crazy enough, ice boxes kind of work everywhere. So that's how much I'm starting with of each. Even if you're not actually using this, like, can I actually use that for a calculation? Why not at least organize your information? Well, if I do this once, just give it a shot. You can use technically pressure molarity in moles in an icebox. You just can't do grams, because you can't compare grams to something else with grams. But even pressure can be related. Like, this will be double the pressure of that if you have the same amount of it. So if I start with that at 0, I don't think what I'm doing here is any kind of a mind blow. Right? That would be the relationships. I'm taking T charts and I'm making it simple by doing that instead. Does it say anything else? No, it does not. After the reaction is complete. All right, which one's going to run out on the left? Who's going to be 0? You know? Because you need twice the amount of this for that, right? So this is all going to be used up. So that means only half of this is going to be used up, right? So what is it actually? X is actually 0.088. So then that means that this will be this. Stay with me. We're almost there now. That was the hard part. 1 point, by the way, is earned for figuring out those moles. Now you could have done this with just a T chart as well and figured it all out, but I thought that was more applicable to some of the things we've done. It asks for the total pressure, you guys. This, it doesn't matter if I'm on the left or the right. These gases exist. They all exist. So when the reaction's done, there's no NO, but now there's O2 and NO2. So I can just do what I did in the beginning. I'm going to take pressure equals total moles, or yeah, pressure equals total moles RT over my V. And that's it. So I'm going to take my pressure, I'm going to take my total moles, and if you're sitting there, valid thing, wait a minute, I have moles, don't I now need to divide by volume and get molarity? You're thinking about aqueous environments. You're thinking about concentrations of ions. We're talking about gas. And that is a very different concept. Where are we at? 298. And I have another 5 to continue. The very fact that they kind of said a different reaction, but then they kind of had remnants of the old one, they should have kind of bumped you to the fact that you probably need to do a PV equals nRT as well. At some point. So 1.29. That's 2 points. 1 point earned for the fact that you found how much gas you have present in moles. And then 1 point earned for the pressure. Okay, let's totally flip gears. No calculators needed. Let's do a little evaluation of some compounds. These are always important to talk about. So this is where I do need, and I know again it seems like we have a little more energy, but you do need to have some conversations or at least compare, come up with something with each other on these, please. So first one, it says structures of pyridine molecule and the benzene molecule are shown below. Pyridine is soluble in water, whereas benzene is not. Those are important things when they tell you these kinds of things. You're not having to interpret that. Come for the difference in solubility, you must discuss both of the substances in your answer. Okay, you don't have to come up with the exact answer written out right away, but what you should do is talk about what both have, okay, and then talk about why that one thing or the other doesn't dissolve in water. Now you can approach it in a couple ways. You can definitely talk about that interaction with water specifically and what water is as well. But you do need to come up with a couple of ideas about what's happening within these, okay? So if you want to make notes even just on your sheet, like, okay, this thing has these, like you can make a list if you'd like. That's what I'm going to do right now to kind of help you with some of your answers. If you want to then compare with someone else, yeah, I came up with these ideas, okay? So we're talking about, well, I don't want to give anything away. So at least write a couple things down, even on your actual sheet or on your work or your loose leaf about just some things that you could apply to these. If you want to start formulating the question or the answer, you can, but at least come up with some. Which one's polar? Pyridine or benzene? Pyridine. So I'm just going to show you some things I just listed. It's not the actual answers yet. But this is polar. This is non-polar. Okay, if you had to explain that, by the way, you never use the word lone pair. It's polar because it has a lone pair. You can start there, but if that's your be-all, end-all, that's not right. It's asymmetrical, right? Or dipoles don't cancel. Those are your two phrases. If you ever need to explain why something's polar or non-polar, that's how you do it. This is very symmetrical. All the dipoles cancel out. So that's how you'd say it. So this is very asymmetrical. Well, not very, but it's enough. I'm gonna write that. What can it do with water? Well, I have N here. What can that do? That can make a H bond. Remember, those aren't actual real bonds, right? Those are, all bonds are just attractive forces. It's not literally a little bridge like someone built and now we're there. It's all attractive forces, but it can make H bond, it can have an H bond with water. It's really important. I'm discussing it with the water. What's going on with the benzene? The best attractive force it has from one benzene to the next, or with water, would be an LD. The minute you say nonpolar, it's LD. It's done. Because there's no charges. You can't make a dipole. You can't be attractive. You can't make an attractive force with the opposite charges, like a magnet kind of idea, right? So what would you have? Here's a way you could write this. There's no attractive how did I write this? Interaction with H2O. Okay. Just giving you some ideas of what you could talk about. I'm going to read what they exactly have, and I'm sure it's in a lot of depth. Sometimes like, whoa, I wouldn't go down any of those paths. I'm in trouble. It says pyridine is polar and capable of forming hydrogen bonds with water, while the nonpolar benzene is not capable of forming hydrogen bonds. Pyridine will dissolve in water because of strong hydrogen bonds that exist between the lone pair of electrons on pyridine's nitrogen atom and the solvent water molecule. No such strong intermolecular interaction can exist between benzene and water, so benzene is insoluble. This is more important to me. 1 point. Where you get points. 1 point is earned for identifying a relevant structural difference between pyridine and benzene. So you could, if you talked about asymmetrical versus being symmetrical, and the fact it's polar and nonpolar, you get a point. Okay. Second point is earned for indicating that pyridine is soluble in water because pyridine can form strong dipole-dipole interactions or hydrogen bonds with water, while benzene cannot. That is the one thing I need you to leave, and we talked about that before. Leave off of it from this question. Is that when you talk about something dissolving in water, you have to literally say that the polar one can make a hydrogen bond with water, while the other one cannot. If you say that, you are going to lock it in. And that, I think we've had that already 3 times, like in the last 2 weeks, like that same kind of idea. So lock that in. Say that, and you're going to be golden. Okay? All right. So that's 2 points. Let's go to our next one. It says structures of dimethyl ether molecule and the ethanol molecule are shown below. The normal boiling point of dimethyl ether is 250, whereas the normal boiling point of ethanol is 351. Account for the difference in boiling points. You must discuss both in your answer. Again, what I would start doing, just make a list or an idea of just at least 1 or 2 things that might apply. If you want to start your sentence right away, you can. Again, my suggestion to you always is, let's just call this A, B, A and B. A has this while B has that. And then you talk about the this or the that. This is stronger or weaker than that, which causes it to have a higher melting point or lower melting point or boiling points or whatever it is. So start off just saying what is present in each, and then move on from there. Remember, it is your job to make the numbers make sense. So you can't be, well, although it's 351, it wouldn't really, that's not true. You have to make the numbers make sense. So these are boiling points. Don't forget what they are also. Just give you a second to at least get your mind set. Maybe you're heading in the right direction already. And you might get this one wrong, the one on the left. I'll ask this right now. Is that LD or dipole? That's what I would see as a student making a mistake. The dimethyl ether. Anybody want to commit? If you're like, wait, I wasn't doing any of that. Well, we're doing phase changes, so we're doing IMFs. Is it symmetrical or not? It's symmetrical, so it would be LD. Okay. I didn't mean to put doubt. All of a sudden, everyone looked like, oh my God, wait, what? But just because that O, people go, well, the O would take from the C. Yeah, but it would take it from the other side as well, and those dipoles would cancel. Okay? It's got to have an asymmetrical field for it not to be LD. Ethanol clearly has what in it? H bonding, right? So to have a stronger boiling point, I'm just giving you thoughts again. What do I need? That means more energy is required. This is a good phrase. More energy is required to overcome the IMFs in a phase change to boil. So would I need a stronger or weaker IMF to have a higher boiling point? I would need to have a stronger one. And this is just generic stuff I'm writing. But that's where you could go with that. The intermolecular forces of attraction among molecules of dimethyl ether consist of London forces and it says and weak dipole-dipole, but it's basically London. In addition to London forces and dipole-dipole interactions, they are comparable in strength to those of dimethyl ether. Ethanol can form hydrogen bonds, getting so specific depths. Hydrogen bonds are particularly strong, so they require more energy to overcome during the boiling process. Phrase those in your own words, but that's the important part. It takes more energy to overcome a stronger IMF. So it takes more energy to overcome a H bond than it does an LD, which causes it to have a higher boiling point. Done. That's where I would end. 1 point is earned for recognizing, I'm not even going to finish reading that part. 1 point is earned for recognizing that ethanol molecules can form H bonds, whereas dimethyl ethers do not form H bonds. That's funny. 1 point is earned for recognizing that compared to the energy required to overcome the weaker IMF in liquid dimethyl ether, more energy is required to overcome the stronger H bond. So it is important when you're talking about phase changes, especially like boiling. You got to put energy in there, right? You got to put temperature. You got to increase that temperature, which is putting energy. The larger the value, it took more energy to overcome it. So it takes more energy to overcome a stronger IMF. That's why that boiling point is higher. Boom. Okay? So that'd be 2 points. Again, a lot of times if it's going to be 2, it's 1 point for just correctly labeling which one's which. But you do it in a sentence, and you do it in your first sentence. The second one just summarizes why that has a higher or lower number that you're looking at. Okay, next ones go a little faster. C, SO2 melts at 201, whereas SiO2 melts at 1883. Woo! Big difference. Count for the difference in melting points. You must discuss both of the substances in your answer. Again, what I would do is make a quick little list or get your mind straight and figure it out, but clearly there's a huge difference between these two. I mean, it's not even close, right? Something should be jumping out. Like the numbers should be like, whoa. Like think about the numbers, but hopefully something spurred you to go. And again, it's still about energy going in. It takes more energy to overcome the stronger one. So I hope we all agree that SiO2 is the stronger force, no matter what, even if I don't know what it is. It takes a lot more energy. The thing is, it's taking a lot more energy. And here's what you will get wrong, actually more than anything. This one. Let's review this quick. Which one would it be, okay? We're going to go full out. We're going to go backwards here. If I talked about valence electrons, they have how many, each of these atoms? They have 6, right? If I'm doing dots, it's good. This is healthy to quickly see. This is 6. This is 6 times 2. So I have 18 valence electrons, okay? I'm not going to sit here and do TV, but I could. Actually, let me just try that once. If you just go out, assume all single bonds, and I'm done. That's what you always do, because more or less times, it's always single bonds. So you could just visually do that. If you do that, how many dots or electrons do I have total counting lines? Do I have 20? Is that 20? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What does that mean? I have 2 more than I'm supposed to, right? So you're like, oh, more dots. Well, no, that doesn't make sense because I have too many. So it's the only other thing I can add. I can either add dots or I can add bonds, right? So I have two too many. So now that becomes this, by the way. It doesn't matter which side I picked. And again, if you're like, how did you know that? Just start putting them down until you get two things, an octet and the right number of electrons. So what shape is that? That's going to be a bent trigonal planar, correct? It's going to look like this. Right? So why am I saying this? Because this thing is polar. If you flatten it out, you would have called these LDs. By the way, if it's an LD, your melting points and everything else are usually really tiny, like in the negatives. So a little hint, some experience that I kind of have where I don't need to like look at a lot of things anymore because I've seen enough of it, is that if it's an LD, that melting point, it's probably not even existing normally as like a liquid in room temps. So that means it's probably, it doesn't take a lot of energy to be a solid or to go from a solid to a liquid to a gas. It's already probably existing as a gas because it's so weak. So this has a dipole. So this is dipole. I just want to make sure we're in the right, because I have a feeling some people would say it's LD. It's not. It's dipole. And what's the other one? What? Oh, so close. Lattice energy is really big, but here's the key to that. It's a good miss that you had. That's a network solid, right? It's a network solid. And that's what the phrase you say. It's a network solid. And all you have to say with that, let me just give you, I haven't read the answer here, but all I know is, I write this down for sure, these have strong covalent bonds. That's a really good way to attack it. You say it takes a lot of energy to break or overcome those strong covalent bonds. And I'm sorry, we might go over about 5 minutes, so I'm really trying. Okay, so let me quick read. Sorry, I've kind of slowed down here. Let me just read what you would have had. 1 point is earned for recognizing that SO2 is a molecules, or it only has a dipole-dipole, while the other point is earned for SiO2 being a covalent network solid. So, just wondering if you really want to hear all this part. It's not that good of an example. Last one, or explanation. So what I would just say is that the melting point, it doesn't take as much energy to overcome the dipole-dipole, while the much stronger covalent bonds require a lot of energy. That's why, or thus, the melting point would be so much higher for SiO2. That's what I would say. Letter D, final one. It says, the normal boiling point for Cl2 is 238. Okay, the normal boiling point of Cl2 is higher than the normal boiling point of HCl. Account for the differences in boiling points based on the types of intermolecular forces in the substances. You must discuss both. Okay, so this is not, this is a great question, because this is, let's just jump into this due to time. That's a London, correct? What's that? It's not H bond. Dipole. Okay, get out of your brains for a second. Clearly, LDs are weaker than dipoles, right? But if you didn't know any of that, which one has the strong, is this boiling points? Is it boiling? I don't want to say it wrong. Is it? What? Don't look at anything else. If I just told you those 238 versus 188, which one has the stronger IMF? The Cl, correct? Right? So you can't be like, and Mr. Anderson, like he's in there, whoever, like, there's a mistake. Hey, everybody, look. And you, and your job is to take, and look at how they worded it. They underlined higher. They're like, it's higher. Trust us, okay? Like, this is a contradictory problem. All you have to do now is say something about why this is higher than that, okay? So let's talk about that. First, this is probably a very weak dipole-dipole. You could say that. Secondly, how do you make an LD the strongest possible? What's the strongest LD? What makes one LD stronger than another? No one? Nope. Size of an atom. Size of the electron cloud. If you knew and didn't say anything, shame on you. So the Cl's big. Cl's big. And you're like, yeah, but the other one's with Cl as well. Yep, but it's with hydrogen, so those electronegativity values are actually quite similar. So let me read you exactly what they have here. It says the intermolecular forces in liquid Cl are London, whereas the intermolecular forces in liquid HCl are dipole-dipole. Since the boiling point is higher, the LD forces among the Cl molecules must be greater than the dipole-dipole forces in HCl. The greater the strength of the London force between Cl2 occurs because Cl has more electrons than HCl, and the strength of the London interaction is proportional to the 1 point is earned for recognizing that the London forces must be larger than the dipole-dipole forces. Okay? 1 point is, I'll repeat that, is recognizing that those forces must be larger, must be stronger, if you will. 1 point is earned for recognizing that the strength of the London forces among the molecules is proportional to the total number of electrons. Okay, so let me just bring that up. That's a little, I don't like that they had that at the end. What suggestion, if you're ever trying to talk about London, though, I think you can get away with this if you talk specifically about the size of the cloud, you're talking about the number of electrons. So that's what they were saying for the second point. By saying you have more electrons in here than in here, because then there's more to interact. Okay? So that's, I think by saying a larger cloud creates a larger LD, I think you'd be fine. And you don't have to get into all the induced dipoles and all that stuff. So, tricky question. I appreciate your patience. We're going to quickly just go through this last one now. All right, so the final one. Again, this is a little old now because we don't do it this way, but I think the follow-up questions and everything else are still really important. These could be parts of any kind of an equation. So let's quickly do these together. It says solid copper sulfate pentahydrate is gently heated. Okay, so I wish we had a little time and I'd let you try to put this all together, but let's just get into it. So that's what it would look like. That's the beginning. I like this one because we haven't seen hydrate for a long time, like actually writing it all out. If it's gently heated, don't overthink this stuff. What happens? We did this in our first chapter 4. It said, which one loses mass because it's gently heated? The water evaporates off of it. Okay, that's all. They're trying to go out of their way, gently heated. So you're like, really? Like that? Like, yep. That's all that one is. The follow-up question is what I actually want to talk about. It says, how many grams of water are present in 1 mole of copper 2 sulfate pentahydrate? Always start, if you don't know what you're doing, always start with your given. So, don't overthink this. For every one of these, right, you got to bring this down. Now, this is a little bothersome. How many of those do I have? For every one compound, how many waters? Don't overthink it. 5, right? Can you get home the grams? Hope you can. Bring the unit down. Finish that off. If you're struggling, I'll fill it in a second. Not that complicated of one. Just good to see some of these. Next one. Okay. Keep pushing this off. So I am now in front of you and ready to show you something. Please underline X as concentrated. Okay? And then underline complex ion. I'm ready to finally, this may come up once. That's the hard part. It's like we can talk about every single thing. Big picture is what's important always. All right, we'll get back to this now. It says X is concentrated aqueous ammonia is added. So ammonia, you need to know ammonia is NH3. There's nothing that you can do if you don't. You got to know ammonia. There's only a couple that you have to kind of have memorized. It's added to a solution of nickel 2 nitrate. Now, I'm telling you now, if you want to write this down, this would have had a phrasing like write the net ionic equation. So I'm just letting you know, because this is a solution. I'll help you out in how I'm going to write this. So this is the NiNO3 2 right here. Okay. They go out of their way to say complex ion, and I really appreciate that they did that. But if they didn't, even then, if it's excess concentrated and it's one of the ligands we learned, usually ammonia. They'll always usually just do ammonia. What you do is either you are breaking up a complex ion or you're making a complex ion. So if you start with a complex ion, something breaks it apart. And I'll show that next week, but this is the one that you need to see for now. So you're making a complex ion. What do we have? There's two parts. There's a transition metal that attaches with a ligand. So I got to use the nickel. Okay, so it's going to take the nickel on this side. Okay, how many ligands attach? What did we learn? Double the charge of the metal. So this is a +2, so I'm going to have 4 ligands. Okay, the ligand is this guy. So here's my NH3, and I'm going to have 4 of them. Okay. Because this doesn't have a charge, right? It's 0. And this one has a +2. This whole thing's +2. The final part, and I hope this makes sense, this has always made sense to me, is if I have a positive, there has to be a negative. Who would its partner be? Who would be attached as the negative ion? The nitrate? Well, if I write, I'm going to write it there, but it's the most soluble polyatomic ion there is, right? So technically, there's a lot of little moving parts here, but that wouldn't be there any longer. So then I just need to balance this, and it's actually not as hard as it looks because there's a 4 right there. So that's creating that. The second part of this that I just wanted to bring up, and it will, if it does, it only comes up once as well. Only comes up once. Underline that, Lewis acid. I will try to bring this up a couple times next week. I'm making sure that the test tomorrow does not have it. This is how I always remember it. A Lewis base, there's always a phrase that was told. A Lewis base has lone pairs, so it gives away, it has extra electrons. Like have a pair, will share is what I learned. Lewis base, have a pair, will share. So it has lone pairs. So it has electrons. This does not have electrons, so no electrons. This is the third way we could call acids. We had Arrhenius acid bases where it gave away H plus or OH minus, and then we learned about Bronson-Lowry where it either gained or lost H plus. There was one more that's really obscure, and it's do you gain or lose H or electrons. So if I gave you enough information for right now, you should really be able to figure it out. On the left side, who doesn't have any electrons, like excess? Who's like electron deficient? So, I mean, if you think about this, that's sitting with electrons, right? That has an actual negative, so it has extra electrons. This is lacking electrons. So this is my Lewis acid. Okay. Well, I'll try to come up with a couple things. Believe me, it's not going to change. If you got a 5, you're going to get a 5. If you're going to get a 2, you're going to get a 2. Not because of Lewis acid bases. It's not going to affect one way or the other. Okay. Final one. Methylamine is added to a solution of hydrochloric acid. Okay. Oh, I hope you may not recognize what this is, but maybe you will. What do you think methylamine is? These are added to each other. They're reacting. What always reacts with an acid? Base. So, again, this is, I'm not trying to throw you off. I'm really not. But if you recognize this, if it says not ionic, I'm trying to show you the hardest way this could be done. I'll leave the Cl there for right now. But really, it would just be H plus because that's the strong acid. I don't even have Cl written on mine. An acid gives away its H, right? gives away its H. So the base gains an H. And again, if I ever have a positive, guys, I need to have a negative lying there. Even if I don't see it, the negative's got to be there. So right now, if I was doing my own paper, I would just cross out Cl because I'm like, oh, the Cl is sitting there on the other side. But just for visual purposes, if you want to see that. I mean, we wouldn't even written that. In the acid bases, guys, we never did. Right? We just wrote it like this. Well, why I figured out, if you didn't, how to do this problem, if you started reading the next one, it asks if it's basic, neutral, or acidic. Oh, this is an acid-base problem. Oh, yeah. So I just add the acid in the base, and this is a strong acid, so I just do H+. Oh, strong base, only OH, right? Okay, so it says methylamine dissolves in water to form a solution. Indicate whether the solution is acidic, basic, or neutral. Last problem, and we are done. This is methylamine. If you react it with water, what's the whole point, guys? If I make H+, it's acidic, right? If I make OH-, it's basic. And the only way to be neutral, the only way from an equation standpoint, is if I did a strong with a strong. So your answer cannot be neutral. This would have to be strong with a strong. Or else you need a lot more information. Like, that's impossible to know. So what does this make? This is acting like a what? This is a base. So already, but you might have to say why. Indicate whether this, well, it doesn't actually say why, but because this is a base, it's going to be added, right? So I'm going to have OH- sit on the right side. So this is definitely basic. Okay? A lot of stuff. Hope it helps. Please let me know if you can't find it, or even if you could. If you do find it, if you want to watch those explanations. They're a little rough. I do it on my laptop at home, and I'm trying to use my finger to draw stuff on the keyboard, grabbing the pen, and it was kind of a disaster. But I do explain all the answers. If you take a little time, at least watch those. It'll help to kind of see where you're at. Okay. Try to be here a couple minutes before 1. We'll be in LGI 1, and we'll take care of it. Thanks for coming in. Really do appreciate it. I hope you feel like it was worth your time.